In this module, we will complete our study of the quantum mechanical treatment of hydrogen atom. As you already know, we started with the electronic Schrodinger equation, and then first we solved for the angular part. And in the last module, we started with the radial part and found out the wave function which was still not normalized using the factorization technique. For a quick recap, let's see that how we proceeded. We had a radial equation which looks like, as you can see here, 1 upon RR del by del R square del RR by del R plus 8 pi square mu R square upon H square E electronics minus V is equal to beta. This is the radial equation with which we started. Here beta was equal to L into L plus 1, which if you remember we got from the corresponding Legendre's equation. Now this radial equation was ultimately reduced to an equation where it could be solved by factorization technique. And the equation to which we reduced this equation was del 2 by del R square plus W plus K by R minus L into L plus 1 upon R square. The whole in parentheses we have FL equals 0. In this equation, as you can see, FL is equal to RR multiplied by R, and then 8 pi square mu upon H square multiplied by E electronics is equal to W, and K is 8 pi square mu upon H square multiplied by ZE square upon 4 pi epsilon 0. So once we reduced radial equation into this equation, then we used the method of factorization to solve it. If you remember, we introduced two factors. One was the creation or step-up operator, and the second was annihilation or step-down operator. Creation operator was RL plus d by dr plus k by 2L minus L by R, whereas RL minus was d by dr minus, in parenthesis we have k by 2L minus L by R parenthesis closed. So using these two operators, we solved the modified radial equation and ultimately we got the radial function. This is RNL max, which is a function of R, and this is equal to n raised to the power n then multiplied by R raised to the power n minus 1 e to the power minus ZR upon Na0. Here L can have the values from 0 to 1 to up to n minus 1. Now for hydrogen atom, Z is equal to 1. Therefore, the corresponding radial function becomes RNL max R is equal to n into R raised to the power n minus 1 e to the power minus R by Na0. Now before we proceed further, let's try to find out the value of the normalization constant n given in this equation. To normalize this radial function, we apply the condition of normalization, and basically, as you know, we had transformed Cartesian coordinates into radial polar coordinates. For these polar coordinates, if you remember, d tau, which is the volume element, is given by r square dr sine theta d theta d phi. R varies from 0 to infinity and theta varies from 0 to pi, whereas the correspondingly phi varies from 0 to 2 pi. Now applying the normalization condition, which is just that the square of this whole function should be equal to 1, we are solving this equation, and you can see that for hydrogen atom n is 1 because Electron is in the ground state, and then the correspondingly L max is 0. So making these substitutions and solving this normalization equation using the standard integral. This is the integral which we very often use in quantum mechanics. We ultimately find, as you can see here, that normalization constant n comes out to be 2 into 1 upon A0 raised to the power 3 by 2. So that's basically the normalization constant. And if now we put it back in the radial function and put the values of n and L max, our final form of the radial function becomes R10R is equal to, we can call it R1s, because R10 corresponds to 1s atomic orbital. So R1s is equal to 2 into 1 upon A0 raised to the power 3 by 2 e to the power minus r by A0. So in this way, we have been also able to get the correspondingly normalized radial function. Now, if you recall what we have done so far in hydrogen atom, we have got every part of the electronic wave function. We have got radial function, we have got theta function, we have got phi function. And in the course of this, we found that 3 quantum numbers emerge, and they have their own significance. One is the principal quantum number n, which varies from 1, 2 and so on. And then is the azimuthal quantum number L, whose values are from 0 to n minus 1, and the magnetic quantum number, whose values vary from minus L to plus L including 0. You also have seen that the principal quantum number primarily determines the energy of the electron in the system. It determines also the average distance of an electron from the nucleus. The orbital motion of an electron around the nucleus is described by the angular momentum of the electron, and the angular momentum of the electron is determined by the azimuthal quantum number. As a matter of fact, the angular momentum is given by L into L plus 1 under root h cross. So here you should see that for hydrogen atom, since L is 0, therefore angular momentum, that means the orbital angular momentum, would be 0. M basically determines the orientation of the orbital, because L, besides determining the orbital angular momentum, also determines the shape of the orbital. Whenever L is 0, the corresponding orbital is S. And whenever L is 1, the corresponding orbital is P, that is the dumbbell, and so on. But what will be the orientation of these orbitals? For S, of course, it's spherically symmetric, so there is no question of orientation. But for p orbitals, that means L is equal to 1, 3 orientations are possible. Similarly, for d orbital, which has the shape of clover leaf, 5 orientations are possible. And these are primarily determined by the 2L plus 1 values of M. Now here I would also like to point out that we have restricted so far our discussion to hydrogen atom. But if we look at hydrogen-like systems or hydrogen-like ions like helium ion or lithium ion, they will also behave like hydrogen atom. Only difference is that the value of Z will change. In hydrogen atom it was 1, it will have 2 for helium ion and 3 for lithium ion. Let's now look at the corresponding radial functions for other atomic orbitals. Now suppose n is 2, then when n is 2, L maximum would become 1. Therefore, the corresponding radial part will be R21R, and that will correspond to 2p, because maximum value of L for n is equal to 2 would be 1, and therefore one can get the corresponding radial function, which is given by n to 1 r e to the power minus zr upon 2a0. Please remember that the formula which we have used for calculating the radial function for 2p orbitals, this is valid only for L max. Now one can say that for n is equal to 2, no doubt L max is 1, but then L is equal to 0 also possible. So how to calculate the radial function for 2s? So that could be the next point. So in order to calculate the radial function for 2s orbitals, we will basically use the property of annihilation operators, which we discussed last time. And that is, we know that FL maximum is given by r raised to the power n e to the power minus zr by na0. Now, if we want to calculate FL max minus 1, that means we want to calculate R20, which will correspond to R2S, then we will use this very important property of the annihilation operator, and that is RL minus FL is equal to FL minus 1. This is a very, very important property. And now if we use this property and solve it, you can see here that if we apply RL max minus on FL max, we should get FL max minus 1. And RL max minus is given by d by dr minus k by 2L max minus L max by r, and then it operates on FL max. So if we make these substitutions and put the value of the FL max as we have done here, and then simplify it, you can see that ultimately we get an expression from which we can calculate F0, that means for 2s, and that will be, as you can see here, which on further simplification gives us this expression, and that is R20R. This is the radial function for 2s atomic orbital. This has been obtained from the radial function for 2p orbital by operating on it with annihilation operator. This is a very, very important thing, and the expression which we get is here, n, then in parentheses we have minus, then in parentheses we have z upon 2s0 plus k by 2 parentheses closed r plus 3, then the parenthesis is closed, then e to the power minus zr upon 2a0. And since we also know that kr upon 2n is zr upon na0, ultimately we get the radial function for 2s orbital, which comes out to be n multiplied by 3, then in parentheses we have 1 minus zr upon 2a0 parenthesis closed e to the power minus zr upon 2a0, where n is the normalization constant. This function can be then normalized. Similarly, one can obtain the radial functions for 3p and 3s orbitals starting from 3d orbitals using the above property of annihilation operator. Now the radial functions for the various atomic orbitals are given in this table. You can see that for 1s there is no direct r dependence. For 2s there is an r term coming. For 3s there is an r square term coming and r also. So this is, you can see a correspondingly the whole set of radial functions for the various orbitals. Once we have got these radial functions, therefore we are now in a position to write the total wave function. You already remember we have already found out an expression for theta function. We have also found out an expression for the phi functions, and ultimately from theta and phi functions we found out the values of y theta phi, which is the spherical harmonics, and we also saw that for s orbitals, that means y 0 0, theta phi is equal to 1 upon under root 4 pi. So using all this, one can say that the total electronic wave function for hydrogen atom becomes 2 into z upon a0 raised to the power 3 by 2 e to the power minus zr by a0 multiplied by 1 upon under root 4 pi. And you can see very well, when n is 1, L is 0, M is 0 and Z is 1, we get ultimately the electronic wave function for the ground state of hydrogen atom. This is 1 upon pi under root, then 1 upon a0 raised to the power 3 by 2 e to the power minus r by a0. This is naturally for n is equal to 1, L is equal to 0, M is equal to 0, and of course Z is equal to 1. If we really want to write down the total electronic wave function for other orbitals, we can write them, and as these are shown here, we can write for 2s, then we can also write this expression for 2p, and then we can also write it for 2p plus 1 and 2p minus 1. So all these expressions you can see here, these are basically the total electronic wave functions, and these are the products of radial part and spherical harmonics. One thing which you notice and which is quite striking is that in the case of 2p orbitals, we use 2px, 2py and 2pz, whereas from quantum mechanics we get 2p0, 2p1 and 2p minus 1. 2p plus 1 and 2p minus 1 contain imaginary quantities. As you can see here, 2p1 has e to the power iota phi, whereas 2p minus 1 has term e to the power minus iota phi. So imaginary quantities will have no meaning, but these two orbitals basically correspond to degenerate energy state. Therefore, we can take linear combinations of these two, and what we get is one linear combination which is 2p1 plus 2p minus 1 divided by 2, and if we solve it, we get, as you can see here, 3 by 8 pi under root sine theta cos phi. Now sine theta cos phi has orientation along x direction, and therefore we call this atomic orbital to be 2px. On the other hand, if we take another linear combination which is 2p1 minus 2p minus 1 divided by 2 iota, then we get, as you can see here, 3 by 8 pi under root sine theta sine phi, and this has orientation along y direction. Therefore, this atomic orbital will be called 2py. So please remember that 2px and 2py are linear combinations of 2p1 and 2p minus 1, and therefore 2px and 2py cannot be assigned any specific single m value. This is very, very important. See, once we have been able to calculate the total electronic wave function, let's now study some properties and the significance of these wave functions. First is, as you already know, wave function is the storehouse of information. And from this wave function, we can calculate various properties of the observables for that system. Let's first calculate the value of the mean radius r. Since radius r or r will not satisfy eigenvalue equation, therefore we will use mean value theorem as we are doing it here. So we have this integral. It is a 3 times integral varying from 0 to 2 pi, 0 to pi, and r will vary from 0 to infinity. So it will be psi 1s, r psi 1s, and then the volume element will be r square dr sine theta d theta d phi. And if we substitute the value of psi 1s, which we have already calculated in this, and then solve this using standard integral, you can see we get average mean radius or average distance of the electron from the nucleus to be 3a0 upon 2z. If z is 1, then it will become 3a0 by 2. Similarly, one can calculate mean radius for other orbitals as well. And the general formula for the mean radius for any orbital denoted by NL will be average value of r, NL is equal to n square, then in parentheses we have 1 plus half, then in parentheses we have 1 minus L into L plus 1 upon n square, parentheses, double parentheses closed, multiplied by A0 by Z. So this is one property which one can very easily calculate. Now in this module, we will study something which is very interesting, and that's basically probability density and radial distribution functions. Now what is that? As you already know, that wave function is basically probability amplitude and it has no physical significance. The quantity which is of some significance is the probability density, which is psi square of the system at a particular point. Now, if we look at the plots of the wave function for the various orbitals with distance, as you can see here, for 1s, we have shown it for 2p, 2s, 3s, 3p, 3d. On the left hand side, we have the variation of the wave function with r, whereas on the right hand side, we have the variation of the psi square, that is the probability density with r. One thing which immediately strikes, if you look at the probability density for 1s, it shows that at r is equal to 0, that means at the nucleus, probability density is maximum. Doesn't it look very strange? How could it be that probability of finding the electron is maximum at the nucleus? This is absurd. Therefore, important to understand why it happens. Please remember that probability density is nothing else but the corresponding probability divided by volume. Now, if we want to calculate probability, then we will have to multiply probability density with volume. Now, if we want to calculate probability at a point in terms of polar coordinates, then we will have to find out the volume element, because hydrogen atom is ultimately spherical. We will have to find out the volume of the shell between the distance r and r plus dr. That will give us the volume element. Therefore, if we do that, it would mean the volume of the external sphere of radius r plus dr minus volume of the internal sphere which is of radius r. And if we do that and subtract, we get the volume element which is ultimately 4 pi r square dr. Now this is the volume element. If this volume element is multiplied by the corresponding probability density, as you can see here, we get PR, that means equals to probability, and that is 4 pi r square psi 1s square dr. This is for the ground state of the hydrogen atom. So now this term 4 pi r square psi 1s square, this will be called radial distribution function. If we want to find out where is the probability of finding the electron maximum, then at that point PR should be maximum. Or PR should be maximum means differential of this with respect to R should be 0. And as you can see here, we are differentiating 4 pi r square psi 1s square dr, that means dpr with r. And once we differentiate it and put it equal to 0, which is the condition for maxima, and then simplify this, we get R is equal to A0 by Z. Or in other words, for hydrogen atom, R will be equal to A0. This is very, very important. If you remember earlier, we found out the average distance. That came out to be different. That came out to be 3 by 2 A0. Here we are finding out the distance where there is a maximum probability of finding the electron, and that is equal to A0, that is the Bohr radius. So this is a very, very important concept, and one should be very, very clear about this. Now if we plot radial distribution function as a function of R for various orbitals, we get the plots as these have been shown here. So in this module, we have completed our study of the hydrogen atom. We normalized the wave function, and radial function was first normalized, and then ultimately we got the total electronic wave function. The normalized radial function for the hydrogen atom was R10R is equal to R1s, that is 2 into 1 upon A0 raised to the power 3 by 2 e to the power minus R by A0. Then we found out the expression for the total electronic wave function for the ground state of the hydrogen atom. That comes out to be psi r theta phi is equal to 1 upon under root pi 1 upon A0 raised to the power 3 by 2 e to the power minus R by A0. We have already got the total electronic energy for hydrogen atom, which depends only on the principal quantum number, and that is equal to minus 2 pi square mu z square e4 upon n square h square 4 pi epsilon 0 whole square. So we also calculated using these total electronic wave functions the average distance, which came out to be 3a0 by 2, and then we also found out the most probable distance, which came out to be a0, and this most probable distance was found out using radial distribution function.